All right, welcome back. So, here's what's going to be on your Chapter 18 test. You're going to have a Charles problem. You'll have a Boyle's problem. You'll have a combined gas law problem. You'll have a ideal gas problem. You'll catch up when I slow down. You'll have to do a problem where you collect the gas over water. Yep. Or maybe two. So there'll be one math problem with each of these, at least. You should know the types of relationships. In other words, like linear, inverse, so remember we drew all those graphs of exponential, inverse, what they all look like. You should be able to graph given two variables. For example, if I asked you to graph V versus T, what would that look like? Oh, let's say the temperature's in Kelvin. If the temperature's in Kelvin, then your graph should go through the origin. And it should be linear. Because when you've reached absolute zero, there is no volume.
Wait, how do you know which one to put on the left and the bottom?
I'm going to provide it to you. So like, I'll give you something like this. And then I'll say, now graph the relationship.
What is combined and normal graph?
So I will have the graph set there for you, and then you'll just have to like draw in the relationship.
Okay. What does combined mean, number 3?
Combined gas law? Just use that one. Yep. I'll let you catch up now.
Are we just supposed to like memorize those like graphs?
Well, that's one way you could do it, or you could think about the labs that we did, or just think about the relationships. If you're squeezing a balloon and making it smaller, what's going to happen to the pressure? It's going to go up, right?
What is collect over water?
If you collect your gas over water, that's when you have to subtract out the vapor pressure.
Are example problems all in the practice test?
Yep.
So wait,
We've drawn all the types of graphs that will be on the test. They're in your notebook. We drew all those graphs. I've drawn those graphs like a million times of V versus T, P versus V. So they're also in your textbook.
Number 6, is that going with number 7?
No, 6 is separate.
I know, but like, it's the linear, like...
So like, what is this graph called? Inverse. What is this graph called?
Linear.
So you should know what the...
Wait, what is an inverse?
Is, we have hyperbola.
Why is that so funny?
All right. Oh, and the last thing, which we have to learn today, is real versus ideal. So real versus ideal gas. And that's what we're going to do right now. Is we're going to do the comparison between ideal gas and real gas.
I love doing these.
So, Braden, you know what wet gas is? That's when you collect it over water. Dry gas is when you don't collect it over water. And now you're going to learn about ideal gas. So, the way I put it is, in our minds, we all have that ideal person we want to meet. You know, they love camping, they like to go for long walks on the beach, their favorite music is Norwegian folk, and they love to do scrapbooking on rainy days. So, who doesn't? So, I hate to break this to you, but that ideal person you have in your head doesn't exist. So, you have to settle for reality. And it's similar in this situation. Ideal gas is what we would really love gases to be like. For example, we would love it if gases were point masses. A point mass means that you have mass but no volume. And I'll keep flipping back and forth between this and my diagram, so don't worry if you don't get it down right away. But when you look at this, pretend the gases have absolutely no volume. They're like tiny little dots. If that's the case, when I compress my gas, I could compress the volume all the way to zero because the gas particles don't take up any volume. Now, obviously that's ridiculous. Gases are spheres. They take up space. And so as you know, when you compress a gas, eventually you're not going to be able to compress it anymore. Okay? So, the ideal world, the real world. So that's what I mean by point mass, is that it has mass, but absolutely no volume. Whereas in reality, they have mass and volume. Number 2, random motion. So when we think about gas particles, your teacher always describes them as just moving around in any old direction. For the most part, their motion is random, but it's not perfectly random. And this is from the fact that gases have a slight attraction for each other. And one of the biggest ones, or culprits, is water. So non-random motion. Suppose you have one water molecule that's going in this direction, and then another water molecule is going in the opposite direction. We'd like to think that their motion is random, that they would just go by each other like that. But what's going to happen when that partial negative gets close to that partial positive? You're going to attract. There's going to be some slight attraction. So as they go by each other, there'll be slight attraction towards each other, and it will change their path. And if the two gases are attracted to each other, they're not going to hit the wall of the container with as much force. So if there's some attraction, it's going to affect the force at which they hit the container, and that is going to reduce your pressure. So it's going to affect the pressure. Third one is elastic collisions. It means that no energy is lost.